my station set up a little bit differently today. I was rendering some videos, and so I don't have my other computer. But so this is a good question. So, right. So there's three. Did I hit record? Let me make sure. Did you guys see it? I'd ask. No, yeah, no, I'm recording good. So there's three things that there's three things that will limit the performance of your battery, right? So we got the kind of equilibrium voltage, right? And that's just if there's no current running, it's just sitting there, right? And so that's kind of the best voltage you can get. The first thing you're going to lose right off the bat is you're going to lose losses to kinetics, right? And that's exactly what kind of Butler-Volmer is trying to capture, is how much voltage are you going to lose from kinetics. The second thing you're going to start losing when you start to go higher currents, you're going to start to lose stuff because of resistance in your cell, right? And that's going to can become significant. But you can generally design for lower resistances, right? So it's typically, you could engineer a lot of them out. And then the last thing is you might have trouble actually getting your reactants to your reactant sites, right? And that's your diffusion losses. And that one can be a little confusing because you can capture that physics in the Nernst equation, which is kind of like an equilibrium equation. But typically we consider it as another overpotential, and we just do the Nernst equation for like bulk. So I know this is probably more than you were actually asking for, but so the voltage of our battery, right, is going to be kind of maybe you could call it like equilibrium voltage, assuming the concentrations are the bulk concentrations, minus the first one you're going to get is your kinetic overpotentials minus your resistance overpotentials minus your diffusion, right? And really, so this equilibrium bulk, right? So this is going to be your kind of your E naught, your standard redox position, your standard redox potential under standard conditions, plus RT over NF, this common term, natural log of the concentration of your reactants in bulk over the concentrations of your reactants, of your products in the bulk. So when I say bulk, I basically mean like if you have some surface and you have some concentration that looks like this is the concentration at the surface. This is the concentration at the bulk in the bulk, right? So it's just, I basically kind of just mean in the middle. But you don't think about it. I see you thinking about it. But this is not the right term, right? Like, you need to put in the concentrations where it reacts. So sometimes we kind of use this because this will be the voltage that you'll see when you first put your cell together. And then you just use this diffusion term, right? And you basically just say, okay, we're going to have this minus RT over NF term, natural log of, in this case, well, you can do the minus. It's just, should I do minus or plus here? I'm gonna do plus, just, and you'll have this term, you'll have your concentration of your reactants at the surface over the concentrations of your reactants and the bulk times the concentration of your products in the bulk over the concentration of your products at the surface. And so when you add these two together, that like natural log of 1 plus natural log of 2, am I gonna do this right? Is going to be equal to the natural log of 1 times 2, right? Mm-hmm. Oh, yeah, that's right, because this is 0. So so basically when you have these two together, you see when you combine them, you just get the Nernst equation, which is actually how we do it. We don't actually really like solve for this overpotential because we basically just say, hey, screw this, like don't bother doing that, because we know when these two terms get added together, you just, this term, this bulk term cancels this bulk term, and this bulk term cancels this bulk term, and you just end up with surface terms, right? So you know that really, so E naught, so we'll say E plus our diffusion over potential is just equal to E naught plus, so this is kind of the confusing one because it gets handled in different ways by different people, but it's really just, concentrations of your reactant at the surface over your products at the surface, right? Mm-hmm. So like this term is just this term. So you can kind of handle those two terms together just with correctly using the Nernst equation, or you can kind of say, hey, I want like kind of this kind of equilibrium when the cell's just sitting still, and then I'll just handle the overpotential as I deplete, as this goes down when I start to react. I can just kind of track it. And so, I don't know, some people like to track that loss, because then they can kind of know, oh, I can see if I flow it faster, I won't have as much of that loss,
Mm-hmm.
So it's just a bookkeeping. It's a bookkeeping thing,
Gotcha.
Do you want to say, you could just keep track of two, or you could say, oh, I have this one part is one and one part is another part is one, right? And tracking how this one changes, So it's like, it's just a bookkeeping thing. So that's not, we haven't even got to your question yet. But I think, so that's the other confusing one. And it has to do with equilibrium. That's the only reason why I started with it. Can I clear all this? Sorry about that.
Yeah.
Give a second. So then we go, so the Butler-Volmer is probably the most complicated one to understand physically. And it really comes down to this diagram that I like to draw. I wish I had a better way of explaining it. But I mean, the way you think, like the way you could think about it, like for example, if you're reacting hydrogen and oxygen, hydrogen plus oxygen, half mole of oxygen making water, right? So you have your hydrogen molecule, right? You have your oxygen molecule, O and O.
Mm-hmm.
Let me bring my dog in. And then you have your water molecule. You have H, H, and O.
H, and O.
No. Okay. No. Let's go. All right. Let's go. Let's go. Yeah. So these are nice. These are like two nice or three nice, pretty stable molecules, right? They're arranged in a way where they can share electrons, in a kind of low energy state, right? So you gotta imagine like somehow this like hydrogen molecule, right? You gotta imagine like somehow you're gonna come in and this oxygen molecule is gonna like attach to it, right? And like has to form something like this, right? And then like another hydrogen molecule is gonna like come off on this, right? And then you'll like gonna like have to like break this bond. So you imagine like this structure is like very unstable. This is like maybe like some intermediate I just made up. And like this is gonna break, and then this kind of has to break, and this has to break, right? Or maybe they all kind of whack together. And then this, you get left with water, right? So you imagine like you can't just go from this plus this to this. these are two, both like, an energy here, and this is like lower, let's say, So you can't
Mm-hmm.
just like go like here to here directly. You have to go into this like weird, crazy state to get the shape that you want, and then it can come down into here. So you can't do this. You have to do this up. This is supposed to be a check mark. You have to do this, and this energy, you lose it, right? So you lose that energy. And so what catalysts help do is they help make this structure favorable, right? They make it so it's not such a bad penalty, right? So you might have like a surface, right? And what you'll come down is, you might get you might get like, your hydrogen molecule and your oxygen molecule that come down, attach onto the surface over here, right? And then maybe, and then, what you can have another hydrogen, right? And so, you can have maybe this surface, and then these can like come and whack onto this oxygen, and these will leave. And then these can all get together, and these can leave, right? And so, like, you imagine kind of the infinite number of chemistries of all the different ways these could react together, But essentially, you need these three atoms to all whack together and stick. And so, what we actually find for these catalysts is you need your products to be able to come down and attach onto the surface, right? Onto these catalysts to help hold them. But you also need them to be able to come and get away. The reactants need to come and attach on the surface easy enough. So like this bond needs to be strong, right? So it comes and attaches easy, so you don't want them to repel. But then your products, whatever your products are, you want them to leave easily. So
Mm-hmm.
this is kind of like it's kind of a Goldilocks scenario with how strongly they bond. So the common thing people say in catalysts is you don't want it to bond too strongly or too weakly. And that's usually because your products and your reactants look similar to each other. So usually the bonding is similar for these two, but it's not always the case. So what you'll typically find is if you plotted like catalytic efficiency or like catalytic capability, I don't know, we could put more numbers, but how good of a catalyst it is, good catalyst being high, you'd have some kind of volcano shape where you'd have some versus binding energy for how strong they bind near, and this would be your kind of optimal, right? It's not binding here, it's binding too strong, right? And so the products can't leave, and so it gets covered in products. Here, you can't even get the reactants on the surface, right? Because the binding energy is too weak. You can't even get your reactants to come and stick.
Mm-hmm.
Um, so that's kind of the physics that we're trying to capture. And so when I draw these diagrams, you can think about it like I'm drawing your reactants here, like your oxygen, maybe your hydrogen and oxygen put together and their energy. And here I'm drawing your products. And so initially when there's no current flowing, an equal amount goes this way and an equal amount goes this way. And the Butler-Volmer really cares about this activation barrier. So it's kind of like this G. You use like G double cross is kind of the usual symbol for this activation barrier. And so, but what happens is when you change the voltage, right? So when you move this down by a certain overpotential, so it goes down to here, and this distance is your kinetic overpotential. When you move it down, you begin to favor this reaction because the barrier for going reactants to products is much, much less than this. And this is supposed to be a Gibbs free energy. That's why it's a G actually. So it's than it is to go from your products to your reactants. Right. And so that will cause forward motion. And so the way, if you do this big derivation about it, you basically say, okay, the current, which is related to the reaction rate. So this is related to the reaction rate, is equal to some exchange current. And so the exchange current is at equilibrium. You have some going right and some going left, equal amounts. And so and the better catalyst will have high exchange current. So it'll allow them to jump back and forth. And that's basically like you can imagine, if you had really you had a catalyst that your energy profiles looked like this, they could jump back and forth a lot, right? They're almost the same. So there's not much barrier. Versus if you had something like this, right? Now it's really hard for them to come and jump up and out of here, right? So the amount of currents would be tiny here, almost zero. So the Butler-Volmer basically has a derivation. It's basically, it sets up this physics and then it does a little bit of derivation about reaction rates related to exponentials to this current. So it's like, it basically says, okay, the right reaction, going to the right, going from products to reactants, the rate is going to be what's the concentration of the reactant times like the exponent of like RT over, oh no, it's going to be this G double star over RT. Sorry, my writing's getting kind of crazy here. And so if you did that and you did the backwards reaction, you could start to, because it's going to be exponentially related to this height. So if you did that, you'd basically get this Butler-Volmer equation. So you have a term with that basically, so you have the concentration of your reactant at the surface over the concentration of your reactant at the bulk. The reason you have this ratio is because I naught has the concentration of the bulk to the alpha power, the concentration of your products in bulk to the alpha power times this K naught. This is kind of a fundamental constant. Doesn't depend, kind of just depends on the materials. Right, and this is times like N and F or something like that. So the reason why you have these, why you have like these terms here is because you see in the I naught you're using the bulk values, and so that'll kind of cancel with this bulk. our bulk here, because then you're gonna have an exponent of what is it? It's like I always forget which one's on top here. It's probably NFE. So it's, yeah, it's going to be NF over potential. So this is over potential. I know my etas look like N's over RT. The way I can kind of tell is I know this is RT is energy, right? And I know this term is also an energy. And I need to take an exponent of it. I need them to cancel because you need it to be unitless. And then we're just going to get minus. So hopefully you have more room than I do. And you're just getting, and this is the forward. So this is the forward part. You just need to go, what's the backwards part? Minus the product at the surface over product in the bulk times exponent of NF. Oh, and there's an alpha in here, sorry. Alpha NF. And I can tell you a little bit about what the alpha is for over RT. Right, so what the alpha is for is because sometimes when you ship, and so this is the Butler-Volmer equation, and we just and we typically ignore the backwards rate to get the Tafel equation, because it's just easier to use, because like right now I can't get the overpotential as a function of the current, which is what I want, right? I want to put in current and I want to get out eta, but because I have it in these two spots, I can't do that. So we typically ignore this term, the right-hand term. Okay, and then I was talking about this alpha. So you could have something where, let's say like this one is super steep and this one is super shallow, right? So maybe the energy profile of your products and your reactants, this is energy profile of your products and your reactants, are not symmetrical. And so what you'll see what you'll see happen here is if you like move this energy down, what you can have is you can have okay, like maybe the energy changes a lot here. So like, or like G double star changes a lot here. So like double plus, and this, the G double star on this side doesn't change as much. I don't know if I didn't really draw it that well, but you can imagine if these are asymmetrical, when you move this down by a certain overpotential, this barrier might change different from the left and right. So this alpha takes into account that asymmetry. And so alpha of 0.5 is if they're symmetrical. And so we usually just assume it's symmetrical. I mean, let's do an extreme case.
And would the alpha depend on like your reactants or what you're using in your cell, or
Yeah.
would it always be you're always kind of guessing on it?
No, totally depends on your reactant, what your reactants are. So let's imagine like this one's parabolic, and let's imagine this one's flat, right? So like, for example, if you move this down, the energy barrier for going left never changes, right? It's always 0. Where this one, if you, however much you move it down by, will change the barrier on the left-hand side. So that's your case of like alpha is like, oh, and by the way, so this should be, and 1 should be like a 1 minus alpha. Sorry. Because, so like, for example, alpha, so like, for example, so that means like the barrier is always 0 going back, and the barrier going to the right linearly depends on how high alpha is. And so this would be a case of like alpha equals 1, right? And then like the opposite case would be like your left is flat and your right is parabolic, right? This is like your alpha equals 0, right? And then like both parabolic is half and half. So the alpha takes that kind of asymmetry of, and these are energy profiles. So imagine like what you want to do is you basically say like, what's the energy of hydrogen? Here's its most stable spot right here. So here's equilibrium of hydrogen, right? You know, and this is like when it's reorganizing to get closer to H2O, how does the energy change, right? So you'd have to know, you know, when it needs to reorganize to go into water, how does the energy change during that reorganization?
Gotcha.
So that's what you need to calculate. And people do calculate this. You imagine, you know, I showed you stuff sitting on the surface. People will calculate a billion different orientations of the molecule and pieces of the molecule to find like the low energy, to try and find the path, the reaction intermediates, to find the path. And there's actually some like the really amazing stuff that comes out of that research. Like, for example, this reaction I talked about here, what you end up having is like, I forget the exact details of it, but you have 2 intermediates like on a surface. You have like, one is like OH, and I forget the other one's like you know, OOH or something. Like you have these two intermediates that you always have in the reaction. And the hard part is that you can never get a surface. So you'd find like for this one, we'll call this A. This will be like intermediate A and intermediate B. So your optimal for A is here. Your optimal for B for your binding energy, right? So like, you know, this might be like, we'll call this, you know, things don't like to bond to lead that much, right? I don't know, what do things really like to, what's a metal that things like typically bind to? I don't know. Things like to react with iron, I guess, right? And here's maybe like platinum, somewhere in the middle, right? So different materials that have different binding energies. And here's your catalytic activity, right? So you imagine for binding to A, your optimal is here. So you want something between platinum and lead. But for B, you need something between platinum and iron. So what the heck do you pick? What the heck do you pick for your catalyst material? Right? Well, it basically says that you get stuck, and like right here in between is your best. So if you did like kind of a combined, it'd probably kind of like, look something like this, right? And so your best would be somewhere here in the middle.
So like,
But it shows you why you cannot do any better than platinum, and you can't reduce the kinetic losses anymore. And so that's why in a fuel cell, people have been trying for, I've been doing this for 15 years. People have been trying to find a better catalyst than platinum, but it's extremely hard. And we still have, we lose, maybe on the order of 30% of our energy in a hydrogen fuel cell because of the kinetics. And it just, because the fundamental chemistry of how it bonds and reacts is just limited. And so that's why I'm not a big fan of fuel. To be honest, is why I'm not a big fan of fuel cells. Besides the other fact that hydrogen is not something that's that easy to store or make. So, but it's like that's like a really powerful result to understand the what's going on. And so an interesting part about it is like plants, though. Like plants can relatively efficiently do photosynthesis, right? Which is not, altogether, it's kind of a similar mechanism. They're like combusting a hydrocarbon with oxygen. And they just have these crazy reaction sites. Like they'll have these proteins that have like, a special binding molecule, a binding spot here, a binding spot here. So you imagine they can have these crazy proteins, to pull in, and, they do so they're typically doing the opposite. They're taking energy in and building stuff up, right? So they're gonna take like a sugar molecule, some like hydrocarbon, some CH. They're gonna take in some oxygen, right? And they're gonna go basically backwards. So they're gonna go, so they're gonna have their what they want is they want to take like oxygen out of the environment plus some like carbon dioxide as like well, they're gonna take CO2. I need to get this straight. I'm not a biology major, and it's showing CO2. What's their hydrogen source? Water. So they're basically doing the opposite. So they're kind of like, they're taking water and CO2 and going back and giving a fuel and oxygen. So you have this like, this, and so you need to basically do the opposite. You need this hydrogen, this water molecule to react the other way. But they have this special system where you imagine you might have like an H, an H, and an O, where you have this special reaction site, which has like 3 different binders in one spot. I don't know if it's 3, but it could have multiple, And so you're not stuck with like as an engineer, we engineer these particles or flat surfaces, right? That's one material. So the hard part about this though, is you have super low surface areas. So your surface areas are low. So you can do it efficiently, but it's like hard to do a lot of it, right? Because you need to make a bunch of these special sites, as opposed to like, we can make with a high surface area particle, we can just make a ton of sites, right? So like there are ways to break this coupling for this oxygen. It's basically, this is just oxygen redox, is what I'd call it. Oxygen redox, OR, right? You're taking oxygen from a 0 state and you're putting it into an O2 minus. So you're trying to put electrons on oxygen basically. And that's just extremely hard to do kinetically. So that's one of the reasons why fuel cells have trouble. So yeah, it's also, it's hard to store and hard to get too. But you see, this is just basically, fuel cells are just one of an infinite number of chemistries you can do electrochemistry with, right? I mean, we have the whole periodic table and the whole combination of different elements in the periodic table to do electrochemistry with. So it's like, it's kind of cool because water is abundant and oxygen's in the environment. I guess, is the natural reason to lean to that one chemistry out of an infinite. But
Hmm.
for me, it's like, I mean, that's the reason why someone came up with lithium batteries, right? It's a, it's a, just a higher energy density, better kinetics system. Um, so, yeah, so that's my long-winded explanation of Butler-Volmer and related topics.
It makes a little more sense.
but I mean, just think about all it is it's like it's just the it's you're trying to calculate what's the penalty for having to rearrange your reactants and then form the products, and you're losing that penalty, and we're just trying to keep track of that. And I mean, the one thing I maybe didn't talk about is like, why does your voltage change your Gibbs free energy, right? But you remember from like this G, you have like the regular Gibbs free energy plus NFE, right? Your voltage. And so that you know that with voltage, you can change the Gibbs free energy of your products or your reactants, right?
Yeah.
Is there a situation where it goes straight into your products, where you have no intermediate in batteries
Um,
and any type of batteries, or is there's always intermediate?
so
Phase?
the simplest type of reaction is what they call an outer sphere electron reaction. So what that basically means, so for example, so that yes, there are some things that like don't have much reorganization, right? So like you imagine something like something like iron. It has all these shells, right? And maybe like you're starting with iron 3 plus, right? And it's going to come down onto a surface. And once it gets close, the electron's going to hop on into this outer shell, and it's going to make Fe2 plus, right? So like that's an example of a reaction, like a pretty simple reaction that didn't require too much rearrangement. There are still kinetic losses associated with this because you imagine the electron cloud does need to change, right? So the molecule, it does need to change some, and there is some reorganization, but like the penalty you'd pay for one of these, like typically, I think for one of these outer sphere reactions would probably be lower than something that requires drastic reorganization. Um,
I see.
but yeah, so there are some that have less, but I don't know. There's probably, there's probably some that have so little that it couldn't really be measured. But I bet you a chemist would make the argument like there's some there. It's just so small, it's not possible to measure. But it's like, but there's probably always some little intermediate state. But it gets hard when you get down to this electron, right? Because like the electron isn't actually like a physical, it acts more like a wave, At least we typically understand it more as a wave than even like a particle and stuff, right? So I don't know. That starts to get beyond my pay grade for my chemistry ability.
How do we measure these? Like, how do you measure the intermediate energy?
So that's the one great part about electrochemistry is like one of maybe the best tools to get at this fundamental physics and to quantify this fundamental physics. And it's why it was probably is like kind of used a lot before we ever talked about energy storage. We used it, as a technique, an analytical technique to know about it. So what you do is first thing you want to make sure is you have no resistance losses and you have no diffusion losses, right? You want to make sure you're only limited by kinetics. And what you can do basically is you can measure your overpotential and you can measure your I, right? And so if you know these two, you can come and you can get your I naught, right? So if you know everything else in here and you measure your overpotential, and so what you typically do, and typically you do these for like large overpotentials, right? So you do like large overpotential, and then you have your current I. And usually you use like log of I. And so what you'll typically have is some curve that's like kind of like, oh wait, sorry. it's going to look something like kind of like this. And so this is like your Tafel slope. This is like where you need Butler-Volmer down in here, where you have low overpotentials. But usually what you'll do is you'll take this line and you'll extend it, and you'll get this part. And this will give you I naught. So this is log of I naught. And so if you did this measurement where you could get rid of the other losses, and usually you do that through 3 electrodes to get rid of like most resistance losses, and you do spinning. So you're doing RDE, rotating disc electrode. So you spin it really fast, and you basically yeah, and so you're basically
removing the other losses.
Yeah, exactly. Removing the other losses so that you know you're only capturing, because you need this overpotential to be the kinetic overpotential. You can't have it be other overpotentials, right? That's the overpotential. And so once you do that, you can fit it. So you see, this is like a really common science and engineering trick is to like, if you have some relationship, right? And you can set up an experiment where you can actually measure some of the items in it, you can come and solve for the last item, right? So that'll actually be, so you'll see a lot of times you'll do measurements and fit the data to get out some of the parameters. Extremely common technique. And same thing with diffusion. So you can also, for diffusion, you can try and ignore the kinetic losses. You can try and remove the kinetic losses and just look at the diffusion losses and then try and get a diffusion coefficient. So like in your electrochemistry setups, especially if it's dissolved, like it might be harder for you, Jose, if it's in the solid, because you can't like manipulate the diffusion that well. Whereas like Nick and Kelly, when they have copper and manganese dissolved in the liquid, they can spin it super fast and just do a ton of convection. So diffusion isn't like that limited, right? But in like the solid, it's a little bit harder because it's harder to do the rotating disc electrode type stuff. Yeah. But we did buy an RDE. There's an RDE waiting on campus for us.
Okay.
So we could begin to do some of these measurements. It should be cool. Yeah, I mean that would be like, really fundamental stuff.
That's pretty cool. I also had there's one article that I couldn't open even with the Global Protect. How do I get access to that?
So there's like I would, if you look up Sharif Fu at our library, so you do like if you just do Cal State LA librarians or something, there's one librarian per college. So there's one for the engineering college, and her name is Sharif Fu. And usually, if you email her, she'll get it loaned from another CSU or find access to it. And I just email, hey, I've used the Global Protect, and it doesn't look like we have access to this journal. You can CC me, like I'm doing electrochemistry research in Dr. Bachman's group. Can you help us get access to it? And usually within a week or so, she'll send you back the article or some link to the article.
Yeah.
Lucky.
All right, keep going. These are good. These are good questions. All right, and you all know, just shoot me an email if if you have questions. Say, hey, I've just been thinking about this. I can't quite figure it out. Let's meet. So I want to confirm kind of our next meeting. So Michael, we're on the books for next Tuesday at 11.
What time zone?
Sorry, my time zone. So that would put it 2 your time.
Yeah, that's fine.
All right, and then Kelly and Nick, we do 12 Pacific. on Tuesdays?
Yes.
And then Jose and David, did we say 1?
1, yeah.
Yeah.
All right. So that sounds good. And then all right. So but then I also have Arnaldo here. Arnaldo, do you want to meet coming up? Arnaldo or I got Arnaldo, Juan, and David also here. So
I think you told us. Well, you told me and David to try to make a meeting with you on Monday. I mean
Okay.
on Friday.
why don't we just schedule something regular on Tuesday? Arnaldo, you want to do that? Or we could just do something Monday this week and then schedule something for later weeks on Tuesday. So Nick and so David, Jose, Nick, Kelly, Michael, if you guys all want to head, feel free. You don't need to. I'm gonna stop the recording.